All right, today's video is on stroboscopes and the persistence of vision. We're going to start with the persistence of vision, which is basically this phenomenon that helps us see motion smoothly. The best way to explain it is think of a flip book. You know how you do this and the pictures sort of seem to move smoothly? The faster you do it, the smoother the picture is. The reason for that is because our brain holds an image of something that we've seen in our brain itself for about 0.1 second after it disappears. So basically this is the time that it takes for our brain to process and then erase that image that was drawn in our brain. So if you see, a car drive by, it looks like it's just going by really, really fast. If it's going really fast, it might even be a blur. That is because our brain is processing slower than the car is driving by, essentially. So it looks as though it's just driving by really, really fast. So that is essentially what persistence of vision is. Now, moving on to stroboscopes. A stroboscope is essentially this device that gives us this periodic flash of light. Like you can see what I drew here. Flashes and then it turns off. Flashes and then it turns off. Flashes, 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 flashes. That's periodic. So the period is how long that light remains off. So if it flashes, because it's a really quick flash, obviously. So it flashes and it stays off for 1 second, the period is 1 second. If it flashes and then it stays off for 2 seconds, then the period is 2 seconds, right? So the period of the stroboscope is how long the light of the stroboscope remains off. So there are some formulas that you need to memorize for stroboscopes, all related to whether the frequency of, so we're going to explain it like this. You have this device here. Let me show you guys. You have this device right here, or not a device, I guess. Let's say a piece of paper with one dot on it, and that dot is spinning. Let's say the frequency of the spinning is 1 hertz. Okay, so the frequency of this thing spinning is 1 hertz. So say the period is 1 over 1 over 1, so the period is also 1 second. So it's spinning, essentially, it takes 1 second for this dot to be back in its place. Now, we have a stroboscope. So make sure you can see that. You have a stroboscope, okay? This stroboscope is flashing also with a frequency of 1 hertz and a period of 1 second. So essentially every 1 second it flashes. So there's a couple rules that we need to learn. First of all, when frequency is equal, let's call this the frequency E, so frequency of the stroboscope, when the two of them are equal, you're only going to see one motionless spot, right? Because if it flashes every 1 second and this is back here every 1 second, it's going to be in the same spot every time. Now, let's say that the frequency of this is higher than the frequency of this. Let's say the frequency of this is 2 hertz, which would make the period 1 over 2 seconds. So every half a second we see it. So in this case, we have FE greater than F. How are we going to see the dots? If you think about it, it's every half a second, right? And this every 1 second is here. So in half a second, where is it going to be? On the opposite side, right here. So we'd see it right here. So basically what we'd see is a dot, a dot, a dot, a dot. But it's moving fast enough that we'd see 2 simultaneous dots. There is a formula right here for this one, for FE is greater than F, which essentially says FE, which is the frequency of the stroboscope, is equal to K times F. Okay, first of all, K belongs to natural numbers, 0 excluded. So 1, 2, 3, and so on and so forth. 0 is not included. K here is the number of dots that we see, which is the dots are going to appear motionless. So if K is 2, we're going to see 2 dots, and the dots are going to be motionless. If K is 3, we will see something like this, where all the dots are motionless. If K is 4, it would look probably something like this, again, where all the dots are motionless, and so on and so forth. Now, what if the frequency of this is faster than the frequency of, or is higher than the frequency of this? So let's say the frequency of this is 2 hertz, which would mean that the period is 1/2 hertz. And the frequency of this is back to 1 with the period at 1. What would that be like? So if the frequency of this is greater than the frequency of this, right? The period's going to be less, meaning we're going to see a number of dots. If the frequency of this is less, it means that the period of this is going to be higher. So if this takes half a second to complete this, but this light only flashes every 1 second, how would we see it? Okay, let's see. Half a second, it's back. And then it goes another half a second, and it's there. That adds up to 1 second. So it flashes when it's back at here. So essentially, if the frequency is if the frequency of this spinning thingy is greater than the frequency of the stroboscope, then we will only see one motionless dot. Does that make sense? It should. If not, rewatch. Now, this one also comes with a formula. And the only different thing about this formula is that these two are switched. So F is equal to K times Fe. Just make sure that's right. Yep. So K belongs to N star. However, no matter what number K is, let's say K is 2, 3, it doesn't matter, we're only going to see one motionless spot, because no matter how many times this turns around or this goes back to its place, we're only going to see it once according to this. Now, there are 3 more formulas. If F is slightly greater than Fe, so let's say Fe is 1 hertz, F is 1.1 hertz, that should be an H, hertz, we're going to see the dot moving with the motion of this. So if you have this right here and it's spinning this way, we're going to see the dot moving like this because of the way the flashes are. Whereas if F is slightly less than Fe, so let's say F is 0.9 hertz, this is 1 hertz, we're going to see the dot moving against the motion. So if the motion is this way, the dot will be moving this way. If either of these cases are true, we can use the formula F apparent is equal to absolute value of F minus Fe. This is essentially just what the frequency that we see is. It's always going to be it should be a little bit slower than this.